So as one may said, some of the things I'm going to present are that they're not exactly confidential information, but they've kind of leaked out a little bit. But they're going to get some big announcements next week at NVIDIA's Envision conference in San Jose. So you'll probably see a lot more information about them then. But you're getting a sneak preview. So after this talk, I'm not going to distribute the slides right away, but I'll give you within a week or so you'll get access to the slides. So for any of you who've seen me give a keynote talk before, I always like to talk about the future of this or the future of that for a couple of reasons. One is that nobody can disagree with me because the future's not here yet. I may be wrong, but you don't know yet. So we'll see. And the other reason is that I can talk about the future of things that I have some part in, so I can make that the future. And I can refine my ideas. So I really look forward to feedback about the things I talk about so that I can make a better future. So this is largely an evangelism kind of role. And you can see I'm in good company with evangelism. This is not a photoshopped image. This is a real banner. And we have the good fortune that CUDA means miracles in Polish. And so there is a movement to try to identify miracles that were performed by the former Pope. But it looks good when you're traveling in Poland that it's truly CUDA everywhere. And everybody's doing it. But the other reason I show this picture is because what I've been doing for the last roughly year and a half is visiting universities all over the world and encouraging them to teach parallel programming more aggressively and to teach CUDA. So evangelism is really what I'm doing. Given the talk that René has seen many times, I've given it about 300 times in the past couple of years. So I'm about done. I think most people have heard the CUDA story by now. So I'll talk about where we're going forward. Through the course of the last couple of lectures, you've gotten this picture, but I have a few slides that kind of state the vision of CUDA and GPU computing relatively succinctly. We have the model of using program kernels and a large number of threads for fast parallel execution. And we're inspired by the way graphics execution proceeds. And we're also inspired by how graphics programmers learn to build their applications. And so we ask programmers to do the work of extracting the parallel portions of their application to execute on the GPU as kernels. And the hardware consumes one kernel at a time, but does many, many parallel things for each kernel. And it's possible to do this because the GPU computing hardware is much different than CPU hardware. We have tremendous amounts of support for hardware threading, hardware scheduling, and hardware management of resources, and relatively little support for memory hierarchies. So the programming model is different, but enables us to support much, much higher efficiency with the transistors. Per transistor, we get a lot more flops. And so for the consumer of these flops, you get more flops per dollar. And really, that's something that we feel is important. So again, and all of you have just spent the last couple of hours hopefully demonstrating this. It's not a really giant step to move from a parallel problem expressed as a loop, as a sequence of operations, to a collection of parallel threads. And it's not even a big change in the code. So it should be relatively easy for many problems to start to be thought of in this way. And we hope we're going to make this a mainstream way of thinking about scientific computing. So the key for us, we thought a lot about whether or not we should take the plunge, jump into the ice-cold water, and jump into the computing market besides building graphics processors. And in doing that, we thought deeply about what would be success factors. How would we build a computing environment that would make a successful product and a successful also computer science and computer engineering tool? So some of the things that we thought were fundamental were building on standard high-level languages, building on languages that people already know. And the starting point was C, and we're moving as rapidly as we can to C++ and to Fortran support. It turns out that the data parallel programming model of CUDA is not that far from the programming model of Fortran 90. You can pretty much translate across almost entirely automatically. So we're very enthusiastic about the opportunities that we'll have with making a Fortran version of CUDA, and that'll be coming out very soon. Also, trying to support standard libraries and domain-specific libraries. It turns out, as probably many of you know, that a lot of scientific computing, a lot of commercial computing runs the same or very similar kinds of codes. And if you figure out a very small handful of commonly used pieces of software to optimize, they can have a really large impact on a lot of people. As we move from small amounts of parallelism to larger amounts of parallelism, it became apparent to us that managing threads and managing resources in hardware was critical. When you have 2 to 4 cores and you have a couple of threads, you can have a software scheduler. When you have tens of thousands of threads on hundreds of cores, everything has to be managed in hardware. And all of the latency and all the overhead has to be automatically hidden by things that the hardware does for you. We would have liked to have built a programming model that was exactly the same as GPU as graphics, but I think we were intellectually honest and we thought that it wouldn't be that useful if we didn't give people the ability to share information between threads and communicate and cooperate. So the whole idea of blocks and synchronization and shared memory is purely a construct that we felt was necessary for more general parallel programming. And finally, all the tools that surround it, the loaders, memory allocation, libraries, resources, are necessary to make a working functional system that everybody can use. And also it's the foundation for a tools ecosystem. If we provide the basics, we can get universities and other companies to build other tool components and make the whole thing more useful. So the programming model you've seen, executing a grid of blocks of threads and only being able to cooperate between threads in a single block is what enables us to build a scalable piece of hardware. We can build small instances that fit in laptops, and we can scale down to handhelds, and we can also scale up to larger systems as well. And I think I'll skip this one entirely because it's the last lecture we gave before this, but the multiple memory spaces give a collection of optimization choices that programmers can make to trade off between ease of access and speed. So I want to describe characteristics of styles of computing on different architectures to illustrate really what's different between CUDA and modern GPU computing compared to historical GPU with the graphics API and CPU parallel computing, or in this case I'm going to give a serial example, but just do it more than once. There's nothing special about parallel computing on the CPU. So if you're building a CPU or if you're building a GPU or if you're building a GPU for GPU computing, you have to solve the same problem. You have a certain amount of silicon and you have to decide how to deploy it to make the best performing kind of processor. So if you're building a CPU, what you build is a very complex control processor, and you spend a relatively small amount of your hardware on the ALU, on the actual arithmetic processor, and you're building a fast sequential engine. And so it's very important that that engine is able to execute the next instruction whenever it's time to go to the next instruction. And so the cache serves the purpose of bringing the data closer to the processor so that you have to wait less if you want to run the next instruction. So the picture that I've drawn here, the CPU, is intended to illustrate that out of the die area, the transistors that you spend on a CPU, you spend relatively little of the circuitry on actually calculating things. You spend most of the circuitry in the actual core on control, and you spend most of the circuitry on the chip as a whole on cache memory. And it turns out to be a good strategy if you have a single task to do. It's a very efficient way of doing that. And so I'm going to give an example of running a fluid algorithm where you have a collection of pressures at different points, and you're going to propagate the pressures to the nearest neighbors, and you're going to do a time series sequence and just keep iterating over time. And what you see if you do this on a CPU is that first time you go through, you'll end up reading all the data from the DRAM into the cache, and it'll be relatively slow. But as you go through the next few iterations, and I'll be charitable, we'll say everything fits in cache, the CPU can run very quickly through the data, and it's actually quite efficient. It's not a bad architecture for solving this problem. But why do people get interested in GPGPU? Well, GPGPU is actually a better strategy for solving this kind of problem. If you look at the way that I've drawn the simplified block diagram for GPGPU, for the tasks that you normally would do for graphics, you end up doing a large set of very similar tasks. So we can spend, as a percentage of chip area, we can spend more area on ALUs and less area on control, because many threads in many processors are doing the same thing, or almost the same thing. So you only need the control to manage the slight differences in the things that the different threads are doing. And with graphics, the access patterns of memory are very unpredictable, and the amount of reuse is relatively small. So a cache doesn't benefit you very much for graphics operations. However, a very high bandwidth and the ability to tolerate large latencies for reading memory is very valuable. So when we map the fluid algorithm to the GPU approach, you end up staging the values that you're going to want to update, and you do a collection of reads, and you request a lot of values, and as you're waiting, you keep requesting more values. When the values start coming in, the ALUs can start processing, start doing the updates, and when they're done, they write all the values back out. And the memory aspect of this, the reuse, is not very efficient. The memory bandwidth is high enough that we can continually stream through all the data. And again, this is a pretty efficient way to run the hardware. And it's actually, it turns out, quite a bit better, maybe 10 to 20 times faster than a CPU implementation. So that's what motivated people to do GPGPU, is you could map your algorithm to get a 10 times speed up. But we observed that there's a lot of wasted effort there because a lot of the data had to be read and written multiple times just because we don't have any place to put it. And nearest neighbors can't share the data, so we have to, in order to do an update, we have to write back to memory. So when we moved to the GPU computing world, as I had said earlier, one of the things we had to add to make a graphics processor a CUDA processor is this hardware management of thread execution. So there's extra hardware, there's extra control to manage the launching and context switching between threads. And there's the shared data area. We have, you can see it's pictured as a very large data here, a very large area on the chip here. And as Wenmei said, there's a lot of registers in these processors, and the shared memory is really a shared register file. So there's a very large amount of area devoted to that. But it's a very effective way to do computation. And we were charitable so far with the first two architectures of assuming everything fits in cache and assuming everything can have its latency hidden by reading. Let's assume everything fits into the shared memory. Every bit of the computation will happen on chip, and most of the chip is ALUs, so you can get a massive improvement in performance over either of the other approaches. This is the kind of architectural approach that can give you hundreds of times speed up on this kind of calculation when you can map it well to the architecture. So we're approaching 100 million GPUs that are capable of running CUDA in the market, and we continue to believe that the right model of doing GPU computing is a heterogeneous model, where we don't replace the CPU, but we collaborate and we cooperate with the CPU. And this has really had a lot of impact on a pretty wide variety of application areas. But it's kind of a chicken and egg problem when you announce, okay, I have a new programming environment, hey, why don't you guys all use it? When you have no install base, it's not very interesting. So what we decided to do about 2 years ago was basically to give a gift to the industry, to the computing industry. And that is that we put CUDA, and CUDA's not free. It takes extra hardware to run CUDA, all that shared memory, all that other hardware. But we put CUDA on every GPU that we built starting in the fall of 2006. So automatically, anytime someone bought a GeForce consumer graphics product or a Quadro professional graphics product or a new brand, Tesla, for high-performance computing, anytime they bought one of these products, CUDA's on there at no additional charge over the graphics technology. So we automatically start accumulating an install base, and now after just under 2 years of shipping CUDA-based products, we have the largest existing parallel programming platform in the world because it's just there. You sneak it into everybody's PC. Sneaky, huh? And this has been very successful. I'm not expecting you to read this eye chart only to see how large it is. When we have people sign up as a registered developer and download the SDK, we ask them what they're doing, and there's a fairly large list of things that people say that they're doing. So there's a lot of different applications, and there's fascinating things that people are doing. We try to analyze this data a little bit, and we categorize it into different kinds of groups, and we also qualify the data in terms of if someone has downloaded the SDK more than once and more than one different version, we consider them to be an active developer. The people who just downloaded it once, they may or may not be, they're not necessarily continuing to work on it. So based on that measure, we expect we have somewhere between 10 and 20,000 active developers, people who are actively writing code in CUDA, and a large variety of different application areas ranging from research to real products. And we are aware of somewhere on the order of 200 to 300 real products that are built using CUDA. And some of the business areas that we see products under development and available are in imaging and video, components for games, computer vision and image recognition. Computational photography is another big area, virus scanning and other kinds of data analysis. I guess I won't go through all these applications, but 2 years ago, I think people would have said, well, there's not really that many useful applications for parallelism on your desktop, but we're starting to see a different view. We're starting to see a lot of interest and a lot of imagination about what you can, if you have 100 times more computing, what could you do that you otherwise couldn't do before? So this is a graph of the downloads of the compiler over time, and this is a smooth moving average because when we do a release, there's always a blip. But I think by smoothing out the average, you can see that we get a pretty steadily growing user community, and each time, over time, we're getting more and more downloads. And it takes a little while to crunch this data, so you can see it's a little bit behind. But I would guess that we're at a pretty steady average of 10 to 15,000 downloads a month. So it's a pretty good base. And hopefully I can take at least a little credit for this evangelism effort, but starting first with the University of Illinois, with WNA, and then a bunch of other schools, we now have close to 100 universities worldwide who are either teaching a CUDA class or teaching a CUDA module in part of their computer science or computer engineering program. So it really is something that we're starting to produce lots of students who have this skill. I think it's an important skill beyond just computing. It's an important skill as a tool for domain scientists. And there's pretty wide developer acceptance. There's a number of products that deliver really unfair speedups over CPUs, and it really drives the business. There are a number of startup companies that have entirely staked their future on their ability to speed up some application based on the GPU. So many of these are available. People who have done something and who sent us a link, sent us information about it, sent us source code. We list them on CUDAZone, which is under nvidia.com/CUDA, and so you can look at all the different things that people are doing. I'm guessing that what we are able to link to on CUDAZone is less than 1% of the things that people are doing out there, but we always encourage people to submit. If you get some good results, share them. It's another place. It's not exactly a publication, but you'll get a lot of reference. You'll get a lot of traffic on this website. So I'm going to go through a handful of examples of things that people have done, and some of them, they may even be people in this room who've done the work. I know one of them, John, I'm going to talk about something that you've worked on, and I'm sure you know more about this than I do. So if people have questions, I may or may not know about the application areas, and if I say anything wrong, I don't mean anything by it. I'm impressed by the numbers without having a full grasp of the details. So one of these is folding at home, which the folks at Stanford had put together, and they really weren't able to write a good folding at home client on the earlier GeForce GPGPU kind of architectures. It was too hard to program. But with CUDA, it's quite easy, and so very rapidly we've gotten into lots of people who have GeForce 8 and GeForce, the next generation of the GTX 280 and 260 products that are doing folding at home. So it's, let's see, looks like about 150 times faster than multi-core CPUs, so a very small number of GPUs. And remember, there's about 10 million GPUs sold a month. Just a few of those people start to participate in folding at home. We're talking about building petaflop supercomputers. I believe that Vijay at Stanford is doing folding at home said that there's approximately 1,000 petaflops of GPU horsepower out there that could be harnessed if people make it available. That's pretty large distributed supercomputer. National Center for Atmospheric Research. It's a real, I want to emphasize about a lot of these are real applications. They're ones that people actually use and do real work with. I was not, before this, I was not familiar with the weather research and forecast model, but I understand it's very widely used. This is work that you've done, right, John? Yeah, so working on a very small amount of the code, less than 1%, gotten a 20% speed up, and I hope that you'll get a chance to do more. So it's very exciting. Not every application is amenable to 100 times speed ups, especially very large real production applications. And so it's actually pretty exciting when you have something real and can get that kind of speed up. A commercial product, not one that necessarily all of us would use, but in Wall Street, one of the important tasks that a trader needs to do is evaluate the volatility of all the options and to decide where's the money opportunity, where's the opportunity to get a large killing. And so this is typically done by a very large cluster of machines in the back room, and it can't be done in real time. It's too much data, it's too much calculation. But it's now possible with 3 GPUs to evaluate the entire US listed option markets, all the options, all the terms, in real time in less than a second. So you can have a continuous display. And in fact, what this picture is showing here is a heat map of where's the most volatility in the options market. So where is the opportunity for trading? So what they did is they actually, to produce this real-time evaluation, you would need 600 CPUs, just for one person doing this, which is 54U of rack space. Moving to doing this with GPUs, we used to only talk to people about how much faster something is than what you did before. But it turns out when people in a research lab or people in a company are looking at the choice between building a GPU computing system and a cluster of CPUs, they're looking at the performance, they're looking at the power, they're looking at the space, and they're looking at the cost. So you multiply all those together. Instead of 100 times benefit, we get hundreds or thousands of times benefits over the CPU solution. So this company is doing very well. They pretty much won't tell us any of their customers, but they order a lot of hardware. So that's how we know. A lot of other more I would say less scientifically inclined kind of applications are picking up on this technology. The clothing design is a surprisingly large application for computational physics. They simulate how clothes will hang as part of the design process, and so cloth physics turns out to be a very, very large application. And this has the benefit of being prototyped at high fidelity in the industry for clothing design, but that same technology is feeding back into the game community so that you can have characters that have clothing that looks realistic. Most of the things that we've talked about, and probably many of you are looking at, are data-intensive and arithmetic-intensive applications. One other area that GPUs are quite powerful is searching and sorting and data analysis kind of applications, where you're digging for something. And you can do a parallel search or you can do a correlation. And GIS systems are one of those. And one of this company, Manifold 8, they have taken a system that was largely batch-based, offline queries, and turned it into a system where almost all the queries are real-time. So you can explore all the physical characteristics of the database. It's just going to change the way people work. In-body astrophysics, I think this was touched on briefly by one of the panelists yesterday. This is a field that GPU computing has had a profound impact on. In fact, it turns out to be a perfect match for the GPU computing architecture. To do the n-body simulation, you have to compare forces from every object against every other object, and you're doing experiments that you can't really do physically, like galaxy formation. It's hard to do that experiment in your lab. That doesn't work very well with a CPU because you end up blowing through whatever size cache you have. However big your cache is, the problem is bigger. So it's very difficult to get very large throughput on a standard CPU. But on a GPU, we can get very close to peak. In fact, we can exceed the performance of custom hardware that was built specifically for this purpose. So several people in this field started using GPUs and presented their results at one of the annual meetings of astrophysicists, and really shook up the community by the results they were able to get. And within 6 months, they organized another conference, which was called Astro GPU, to teach all the astrophysicists how to use GPUs. And from what I understand, a normal international astrophysics meeting is less than 100 people. It's a fairly tight-knit community. This Astro GPU conference was several hundred people, all packed into a room that was planned for about 100 people. Pardon me? Okay, and I think, were you there? So fantastic level of excitement. And now pretty much every paper that where people are really looking at large-scale results, they're using GPUs because you can't afford not to. It's 100 times faster. Now, even more important for us, when I talk about GPU computing, people ask me, well, do you guys use it? Well, it turns out now we do use it. People have started to develop applications on GPUs that will enable us to do a better job of building GPUs. And so the first one of these is circuit simulation. And it turns out that as we build more and more complex circuits, the accuracy of our transistor evaluation, accuracy of the circuit approximation has to get better and better so that you still get a reasonable answer for the whole circuit. So in some cases, most of your time is spent doing this transistor evaluation, and we're able to get a fairly large amount of parallelism and a pretty good speed up. So this company, Nacentric, is doing a tremendous job of using GPUs to speed up SPICE, which is an enormous benefit for us. You think about the amount of rack space we have for our data center, it's about, I would say, 10 or 15 times the space of this room. If we can improve our performance per space by a factor of 8, that's very valuable. Cost aside, just the space is worthwhile. In Silicon Valley, space is expensive. Another piece of technology that we will be able to make great use of is for optical proximity correction. And in modern semiconductor manufacturing, the manufacturers are using light to print circuits that are smaller than the wavelength of the light. And they're doing that by doing the reverse calculation of the diffraction of the projection of the mask onto the surface and calculating the shape to project that will produce the right pattern once it's diffracted onto the circuit. And you do that, in our case, for 1.4 billion transistors. And this takes a long time. Actually, with thousands of CPUs, it takes months to do that for one of our chips. So we could be completely done with the design and ready to manufacture it, and we have to make the mask to print the circuits, and it takes several months of thousands of CPUs crunching on it to produce the pattern. Doing it on GPUs hundreds of times faster, it's not only less expensive, but it's much more effective for time to market, so we can actually build a chip while it's still not obsolete. Which is a real problem in graphics. When your life cycles are 6 months, you don't have any time to lose. Another application is there's a startup company called Evolved Machines, and they're doing a computational model of neurons and the way that nerve cells form connections with each other. And they want to use that model, although it would be an interesting thing to study on its own, they want to use that to build systems that can do early vision and early olfactory sense of smell kind of sensing, and for things like image recognition or recognizing explosives or toxic chemicals. And doing this level of simulation is very complex, but there's a lot of parallelism in it, so it's something that maps very, very well to GPU computing. Now, fortunately or unfortunately, many scientists don't program. Lots of scientists use other tools, and we'll do some amount of scripting, and we'll embed the calculations in some tool. So one example of that is MATLAB. There are far more MATLAB users than there are C programmers. And we have the ability to take tools like that and embed CUDA libraries in the tool. So we took some of the MATLAB functions and implemented CUDA versions of them, and now you can take various MATLAB applications, and they just get faster. The person who's using it doesn't have to do anything except install the library, and it automatically gets sped up. I think this, in some ways, will have an even bigger impact than the widespread use of parallelism to write parallel applications. So I've been talking about making things go faster, because that's near and dear to my heart. That's what we've been doing for a lot of years, is making things twice as fast every 6 months. But I want to talk about the nature of faster. What does it really mean? So 2 to 3 times faster is really what we've been getting for the free lunch of Moore's Law for a lot of years. Every 2 years, you got a CPU that was twice as fast, and you didn't have to do anything. It was easy. And I will argue that over time, integrated over a bunch of years, that's really exciting. But one shot, two times faster, it's not really that exciting. You can do a little bit more. You might wait a little less long, but it doesn't really change anything. It doesn't enable anything drastically different. It doesn't change how you work. It doesn't change the way you would do science. 5 to 10 times faster is actually significant. It's going to make a difference for you. You can start to look at bigger problems. You can start to really take a bigger bite out of your scientific realm. And for 5 to 10 times faster, you'd actually proactively upgrade your machine. You might rewrite pieces of your application. But another order of magnitude, 100 times faster or even more than that, really is fundamentally different. You're no longer doing the same thing anymore. You would consider a whole new platform, a whole new way of computing, a whole new way of building your application, because this makes entirely new applications possible. If you are doing a task that has to run for months or weeks, when you make it 100 times faster, you can start to learn a lot more because you can run more often. You can also run much larger problems and get a deeper understanding. You can go back and re-examine the assumptions that you made to get things to run in the first place. And I think that this is a fundamental change for science. If we can drive 100 times speedups very broadly, it's really going to drive time to discovery and increase the rate of fundamental changes happening in science. So now we're going to move into the future. I'm going to talk about how we get to these kind of speedups. Tesla T10 is the next generation computing product. We've announced the consumer version of this. It's the GeForce GTX 280. And it's approximately twice the performance of the previous generation on almost every application that we measure. And on some applications, it's even better than that. And just to show you the simplified diagram I showed for you before of what a processor looks like and how much cache there is and all that, this is one of our processors. This is an array of processors, and this is the cluster you saw, the two SMs together. So most of the chip is processing. And this product, so Tesla 8, by the way, is the GeForce 8000, or the first Tesla product family. This new chip has roughly twice the peak throughput, more than twice the physical memory, up to 4 gigabytes, and this is a market slide. It's funny, double the precision. It's like double your flavor. But it's the first chip that we support double precision, and so for applications that require that, it's not just double, it's a capability that didn't even exist before. And we still maintain, double precision is slower than single precision, but we still maintain the ability to do very, very high performance single precision. So I think one of the things we'll see is some hybrid algorithms where people use double precision just when they need it, and use single precision for the bulk of the calculations, because a lot of data, the source data isn't even single precision detailed, so there's really no point in doing double precision math on 8-bit source data. And another thing that I started promising several years ago, and we've been gradually delivering, is from the moment that we first started supporting floating point on GPUs, we did not implement the full IEEE floating point spec, but we have gradually been improving our implementation, and now since GeForce 8 we're at full precision. We're now supporting all of the rounding modes. We now are supporting denorm numbers, which we did not before, at full speed. We have actually pretty much support for all the features except for flags and exceptions, and it won't be too long, I predict, before we get to those. But at the point we are now, there are fewer and fewer people who are concerned about the parts that we don't support. We retain the advantages that we've had for a long time of doing reciprocal and square root and the trigonometric functions. Our hardware estimates are much more bits per cycle than they're able to do with a CPU, so we have much greater throughput for those kind of functions. And we've actually tested this new architecture on a lot of applications, and some of these are performance and some of them are time. So some of them, the larger bar is better, some of them, the smaller bar is better, but take my word for it, for all these different applications, we're approximately twice as fast, and in some cases a lot more than that. And the reason for that is, in this particular case, the reverse time migration, a seismic application, we would be approximately twice as fast for the same memory size, but having a much larger memory, we're able to get much more throughput because we can amortize more of the data transfer over the computation time. So how do we get to 100 times? Well, if you look at how you build a traditional cluster in a data center, let's say out of commodity parts, you might build your nodes out of quad-core CPUs, a couple of chips per node, and you'll end up with thousands of cores, thousands of servers, and if you need more performance, you just add more racks, and more power and more money. Don't forget those parts. As you go forward in time, though, I think you're going to see this diagram's a little funny when they point it out. So I'm going to talk about the blue part and the green part separately, just ignore the fact that they overlap on each other because they're not on the same relative scale. One of the things that we see with multi-core CPUs is as you add more cores, the communication costs between the cores and the structure and the architecture of the cache begin to interfere with your scaling. So it's possible to get good scaling up to 4 cores. It's harder to get up to 8. There's some not very widely publicized data from some of the CPU manufacturers that the larger numbers are even worse. In fact, this is a very generous graph. On many applications, the performance actually goes down because the communication begins to dominate over the calculation. With the GPU, with the CUDA scalable programming model, we're able to scale up and down to a much larger number of processors. And we've already demonstrated with the G80 family, where we ship between 16 and 128 processors, and we get perfect linear scaling. And now with the Tesla 10 processor, we're able to demonstrate up to 240 processors with linear scaling. So we feel we have quite a bit of headroom up to much larger numbers. So this is another way to build a cluster. You can take the same CPU-based host system for your cluster, but you can also provide GPU computing attached to those CPU hosts, and we build GPU 1U racks that have multiple GPUs in them. We have had, so far we've built with G80, the GeForce 8, which is approximately 2 teraflops per U, because we can put 4 of them in a single U. We will be building racks with 4 and 8 of the Tesla 10 processors, which will be 2 and 4 times respectively. So we'll be able to get almost 2,000 processors in a single U, and much higher computing density. And this list here of universities and companies are ones that are already on the path toward building these kinds of clusters. About half of them have already been built, and the other ones are in process. So this is really a pretty exciting technology change in terms of how much performance for power, for space, for dollars you can get. So if you wanted to build a 100 teraflop data center right now, entirely out of CPUs, you would need about 1,500 CPUs, CPU chips, and that would be about $3 million, and that would be about a half a terawatt of power consumption. If you were going to build the same level of performance from GPUs, you would need a lot fewer chips because you have a lot more performance per core and a lot more cores per chip. And so getting to the same level, you could do the same thing with 25 CPU hosts and 25 Tesla racks. So that would be 10 times lower cost and 20 times lower power, same overall performance. And you could fit that in a single rack as opposed to, I don't know how many racks the other one would be. So it's pretty exciting in terms of departmental servers, in terms of what you can build in a distributed fashion. So this is the hardware that makes that possible, and this is a product that has been announced but not released yet, and it's the new chip version of the Tesla product that we had built earlier this year. So in a typical server room form factor, we can put 4 teraflops per U. That's pretty amazing. We also can provide that for a single slot version for PC. And in fact, we have had several people build a visual supercomputer or a personal supercomputer by putting 4 or 8 GPU cards in a single box. And there's a recent article, I forget the institution, but one of the universities in Europe built a box they called Fastra. And it has 8 GPUs in a single box. And it performs, so it cost them about $10,000. I think they said 5,000 euros, but that box performs at the same level as a supercomputer that they had just installed and inaugurated that cost them about 3 million euros. So it's a I guess it's exciting, but it's also a little embarrassing for the people who funded the big supercomputer. And I think we'll see a lot more of that. I talk about the large-scale cluster where you can build a lot of teraflops in a bunch of racks, but and that's significant. That's really important. I don't want to minimize the impact of that. But the even bigger impact is taking the performance that used to be the scale of the departmental cluster and bringing that to the desktop of all the scientists. So everybody can have a teraflop, and in a year or so, everybody can have 10 teraflops, and that really is going to drive the amount of experimentation and exploration that people can do. So what's next for CUDA? I mentioned already support for Fortran, support for C++. I think another piece of technology that's going to be very important for us is better and more transparent support for multiple GPUs. So if you're a gamer, by the way, how many people here play video games? All right, good. That's pretty good. You guys already know this. You can take 2 GPUs and plug them into your PC, and your game runs twice as fast. How cool is that? You just plug it in and it works. Well, if you're running a CUDA application and you get 2 GPUs and you plug the second one in, your game runs, your application runs not any faster unless you change the code. So we need to do some work to make the programming environment and the tools scale automatically or scale easily in the same way that we do with SLI for gamers. Because really, what a great thing. You're doing a computation for your publication, and you realize that your computation is not going to finish for 2 weeks, but you have to publish it in a week. So buy 2 more GPUs and plug them in, and you get it done in 4 days, and then you can make your deadline. I know this will happen. So we want to be a part of that success. The other thing that we've talked about is debugging and profiling, which is very hard for parallel. And we've been progressively putting more hardware support for that. You now can, with the newer hardware, you can single step and do symbolic debugging. You can examine and set any variable anywhere in the kernel, and you can profile. You can find out where you're spending all your time. We also are providing support for, I talked a little bit about it with the when you rack boxes, but support for building GPU clusters, tools, and kits. So 10 teraflop, instant 10 teraflop, just add a rack. And those are the kind of things that we need to build. Some of the other things that we need to build, and are not on this slide because this is an official marketing approved slide, that are things that are in our roadmap. So I'll talk about the future that's not written down. And the research community at the universities plays a very important role in this, and some of the work that Wenmei and his team have done have led to some of the things that we're already doing. We need to look at the CUDA programming model and make it more accessible, make a higher level of abstraction so that the entry is easier. I already feel that the CUDA, because it's just C, it's based on standard C, is very accessible. It requires some learning, but you guys will be pretty good by the end of the week, so it's not that high of a bar. Although you guys are pretty smart, so maybe it's not for everybody. The thing we need to do is make it much more accessible and much lower barrier to entry so that the parallelism can get much more broadly accessed and much more easily exploited by people who, for many scientists, a computer is like a pencil. It's not interesting, it's just a tool that they use to do something else. So the easier programming is, the more accessible it is, the more valuable it is to them. So some of the things that we have in process are improvements in our tool chain. And this is a picture, you've seen a different version of it, but it's essentially the same tool chain picture that Wenmei showed. You write your application in C or C++-like form. You can make use of the libraries that we've already built, and you have a system with a GPU connected to the CPU core with PCI Express. You run through the compiler and the tools, and you have access to all these cores, and you're running on the CPU, you're running on the GPU, you're doing all this stuff together. But that tool chain presupposes that you have a GPU, and really the output that we produce for the device is purely for the GPU, so that limits us. This comes back to the question that was asked earlier about, will I mention ATI? I won't mention ATI, but I'll mention AMD. Anyone who builds processors ought to be able to build a CUDA target, and we decided to go ahead and help with that. So, is my laptop awake here? There we go. So we built a set of tools based on some research that Wenmei and his students had done to target multi-core CPUs with CUDA. So in CUDA 2.0, we'll be releasing a version where you write your CUDA program and you can either have it output code for running on the CPU and the GPU with the device being executed by the GPU, or you can generate code that will run on the CPU as well if you don't have a GPU. So now really, truly, we have CUDA everywhere. So we will support not only the GPU many-core, but with a command line option in the toolchain, support generation of multi-core CPU code. And again, once you've gone to the trouble of organizing your data and organizing your task execution so that it works well with hundreds of cores and thousands of threads, it actually is a really good fit for a few cores and a few threads. It works out quite well and it's very efficient and nearly linear scaling. So that's part of our effort to make CUDA everywhere, and I appreciate your help in this effort, and thanks for listening.
We do have time for some questions, so we start at 5:30. So David, I'll just let you go ahead and take questions.
Quick one about the Tesla C1060. Does it have graphics in built in, or is it just a compute device?
So the question is, for the Tesla 1060, does it have graphics built in, or is it just a compute device? It doesn't have graphics connectors. And it doesn't have the professional OpenGL acceleration that the Quadro product line has. But you can run retained mode graphics. So in other words, you can make the API calls, compute a picture, and read it back. So if you wanted to do offline rendering, you can do that. But you have no way of getting it to a screen because there's no connectors.
And just one quick one. Do you know the price range of that 100
I don't. And if I did, I couldn't tell you because it hasn't been released yet.
So when you start talking about teraflops and petaflops, you're definitely talking about competing with a very different market, high-end supercomputing building companies. And we talked offline the other day, said right now you have 3 support people in total for the CUDA user community. And so I guess I don't see that meshing. So will NVIDIA add to the support for CUDA as they make more inroads into the high-performance computing community, or will they just say users, figure it out, or go with some of that?
Okay, so the question is about, we move into high-performance computing, we need to raise our standards to a whole higher level of support. Is that a good paraphrase of the question?
Well, it would seem that IBM and Intel need to do a whole lot more support to support their supercomputing users, so I believe that they're not wasting money there.
So I want to make a comment, and just it's a point of view comment, and this is for me speaking personally, not speaking for NVIDIA as a company. If CUDA and GPU computing becomes used pervasively by scientists and engineers in their laptops and workstations, the entire supercomputing community would be collateral damage. It's a really small market in terms of the number of chips. It's just really tiny. If you just add up the number of processors that are in supercomputers and the number of processors that are in mass market products. So the picture that I have is not of supercomputers as a separate, unique market. I see the whole picture as vertically integrated. And for me, it goes down to handheld devices, to netbooks, to laptops, to desktops, to workstations, to desk-side clusters, to departmental clusters, all the way up to really large-scale installations. So the support for all of those needs to be integrated, and it needs to build on each other. The way that support is done for a mass market product cannot be one-to-one because there's too many people, there's too many users. It's one to many, and it's structured based on forums, it's structured based on reuse and blogs and user communities, and there can be a small number of people managing that and guiding it, but it can actually be much more effective than having hundreds of support people answering phone calls and answering emails. That being said, for professional customers, we're a company who loves our customers just as much as any other company. And for vertical markets, specific application areas, we do have people who support those businesses. You asked about support, and I said 3 people. That's for academic. So the university efforts that we make, the support actually gets integrated a lot more into university online communities. And in fact, I mentioned CUDA-Zone, but in a lot of the countries that don't speak English, there's a university that runs the support website for us in exchange for some other benefits. So there's a lot of different ways to do support. And so now, that was all kind of, that's my opinions about this. From the company point of view, if there's big business in building supercomputers, I'm sure we can afford more support people. That's not the bottleneck. That's not the problem. But really, pervasive supercomputing and personal supercomputing to me is a much more exciting revolution.
So I heard that Intel's coming out with a defined CPU GPU that won't require any sort of special interface like CUDA. So what's the advantage of using it outside that's available now as opposed to say 2009 or 10 or whatever that would be?
So don't underestimate the inherent advantage of existence. So the question was about Intel producing an integrated CPU, GPU that doesn't require something like CUDA. If you interpret that comment naively, so they're going to build a parallel processor that doesn't require a parallel programming environment, good luck. I think that Intel's a company full of really smart people, but it's a big problem to build an environment that works well with a complex, heterogeneous parallel computer. And I think that they're honestly playing catch up against CUDA, which is a very popular environment. And if they come out with a product in 2010, we will have built 4 more product cycles by then. So I welcome them to the world of parallel computing when they get here. So the question is, when we do the automatic translation of CUDA for multi-core, how much of the peak of the CPU do we get? The first caveat is that when people are writing code for CPUs, it's very hard to get anything like the peak performance to begin with, even if they're writing single-threaded, single-core code, for example, things like taking advantage of SSE. But notwithstanding that part, we actually find that we get pretty good scaling because the CUDA code is very well behaved in terms of consuming the CPU resources. It's actually, in some ways, a less constrained environment with the cache structure than the GPU. And one other thing that we find is the process of converting code to CUDA, which is identifying the massive amounts of parallelism that are present in the application, if they are present in the application, produces a much better balanced parallel implementation than the by hand conversion that people typically do when they take their program and they convert it to run on multi-core. So comparing the automatically, converting by hand to CUDA and then automatically converting back to multi-core often produces a better result than converting by hand from single-threaded to multi-core. So by that measure, more than 100% efficient.
For some problems, how many types of using a large computers that's very large memory? That's something you address is sort of how does memory compare, how memory becomes class. So you have the same performance, but one kind of memory has problems.
So the question was about large memories for large computer installations, and do we have the capability of doing that? It's certainly possible that we can build GPU cards with much larger amounts of memory if that's an interesting market. If people, we're happy to build anything people want to buy. So that's not bad.
I guess what is the current product? What is the memory?
So the G80 product was 1.5 gigabytes per GPU. The Tesla 10 product is 4 gigabytes per GPU. And it doesn't preclude having a host system which has a very large memory backing store. Remember the comments earlier that the distance between the memory and the CPU is not shorter than the distance between the system memory and the GPU. So that's part of the GPU's memory system if you build a host with a large memory. So it's really kind of orthogonal.
But you're reducing the number of nodes, CPU nodes, that you break.
Okay, so you can have more memory per node, which is better anyway. Because one of the things we find when you begin to scale up to these massive performance levels 100 times faster is the weak link in a large cluster is the network. InfiniBand is nowhere near adequate for this kind of computation level.
So the programming model for these larger clusters is MPI plus CUDA at the local level.
That's right. Okay. The question was the programming model for the large clusters is MPI plus CUDA, and that's a valid programming model. That's another area that we could innovate. So.
Will you comment on the future and position of the GPUs and the DSP chips, like PIs on some of the applications related to the overlapping? So comment on that.
The question was about the overlapping between DSP chips and GPU for application areas. I guess DSP chips are it's a fairly successful business. I don't know the size of it, but I think that the homes, the places where DSPs find a place, are much more in embedded kind of products and less in general purpose computing kind of environments. And I think a big part of that is the programming model. And in some ways, This is it's an interesting conversation. This is one of the questions I get often. So why are GPUs better than, I'm going to fill in the blank. One of the things that goes in the blank is the cell processor, FPGAs, DSPs, multi-core CPUs, some future architecture that Intel's going to build. And these questions all get asked. And really the answer is, comes in many forms. One is pervasiveness. We hide a free CUDA processor in every graphics processor. So everybody who has a PC with NVIDIA graphics has CUDA. And not everybody has a DSP necessarily, or it's not exposed. And the combination of that and a relatively accessible programming model and a roadmap where we scale regularly, I think is a very powerful combination. It makes it create a lot of excitement. That I honestly, I don't think you could go to all the chemists and biologists and get them excited about using DSPs or FPGAs, but you can get them excited about using GPUs.
What you have at this point, I think, is a de facto standard. Like, NVIDIA does a good job at that. Have a good jump on it, and CUDA could become a de facto standard. I'm wondering, would NVIDIA participate in or even lead a more formal standardization of, you say CUDA everywhere, that would imply at some point API would support CUDA or vendor X would support CUDA. That would entail people getting together in some kind of more formal standards committee, such as what we've done with FDI, to actually come up with a standard like FDI. Would NVIDIA do that?
So the question is, would NVIDIA consider making CUDA a standard or participating in a standards body that wants to standardize the technology? And the answer is yes, we already are participating in a couple of efforts. There's an initiative that Apple has been driving for OpenCU, which is a non-proprietary open standard for computing, which includes GPUs and other accelerators. And NVIDIA is part of that. In fact, since OpenCU is a subset of CUDA, we will probably ship the first implementation of it, because all we have to do is stub out about half of CUDA, and then we're shipping OpenCU. So that has potential. From the point of view of will we standardize or will we open source CUDA, I know it's not the question you asked, but it's another related kind of question. To some extent, there is value for NVIDIA to control our own fate, to be able to innovate both in hardware and software and build a programming model and build the hardware to support it. So I see CUDA as a proprietary standard. What that means, by the way, Java is a proprietary standard. It does not prevent wide use, but it does prevent pollution and fragmentation. And it allows you to maintain a useful and effective and broad programming environment. And we already, I don't speak of ATI anymore because the company doesn't exist. It's part of AMD. So we already support AMD processors, and we already support Intel processors. So if they have a published instruction set and it has enough capability, we can choose to support anybody. And we've also open sourced some of our tools, and we've made public the spec, so it's possible for them to support CUDA on their hardware as well. It's not possible to really be more open than that, unless you say, here, take my standard and mess it up. You could do that. That would be more open, but it would be less useful, I think. So,
As you get to the new generation of Tesla, where you have 18 GPUs in the box, could you say something about, do you anticipate something like PCIe being a real bottleneck for your development, where you want to have 8 or 16 or 32 graphics cards per system? Do you need to develop a new bus, or basically, is there a point we're going to quickly reach where the CPU is now a bottleneck that you need to start doing other people's work for too?
So the question was about boxes that have 8 GPUs or more in them, or whatever number. Is PCI Express going to become a problem, and do we need to develop some other kind of interconnect standard? First of all, I probably wasn't quite clear about the box with the GPUs in it. The first boxes will have 4 GPUs. I mentioned that we could go to 8. It's not something we've committed to do. Just the hypothetical, how do you make 100 teraflops in a rack? I needed another doubling, so I had to postulate that you could put 8 GPUs in one U. PCI Express is an evolving standard. And we've gone from Gen 1 to Gen 2, and there's a Gen 3 that is proposed. I mentioned a couple times, and it's an enduring myth. It's not the biggest bottleneck in the system. It's not the worst problem that you face in scaling a computer system. That being said, as we go forward to larger heterogeneous kind of processor systems, I think there will be much more high bandwidth and coherent kind of interconnect protocols. And as those happen, they will either be proprietary. Some companies will develop their own things, like they have front-side buses and front-side bus licenses that they don't tell anybody about. Those can always be reverse engineered, and there's nothing to stop that. But I think there also will be open and standard kind of interconnects. So PCI Express is just today. Tomorrow is something else, and I don't even know what it is. But if it's more than a year away, then it's something that we'll co-develop with other people in the industry. So, question there.
Are there plans to support concurrent execution of multiple kernels?
The question is, are there plans to support concurrent execution of multiple kernels in CUDA? The hardware already has the capability to do that. The challenge is building an API and a programming model where people can not hurt themselves too much. So we're working on that. There's some things that you can do that make it very easy for people to write code that won't work. So we want to really think carefully about what capabilities we expose, so that they're things that we can really guarantee that people will have a good experience with it, and it's something that we can provide upwardly compatible support for as we go forward. Once we expose a feature, we have to support it forever.
Can you ask me how long before something like that might be?
I can't, because I didn't even say we were going to do it. So it really is a question of finding the right programming model so that you can guarantee that it will work well for people.
You said before that you chose to go with C because it was around, and you chose to go with programming because it was less. But you also said a little earlier that you're getting to the point where you want to make it easier to handle, and not many people have no C when they're not level. So another thing you said was that originally you were thinking that there's a lot of people who want to go for it, making your own language. Did that issue on the table again, now seeing how it's developed, or is it that on the shelf with a forward future new language?
For us to invent a new language? I don't think we're in that business. And I don't think we have that expertise necessarily, but I guess, I'm sorry, I didn't repeat the question. So the question was about, we support C, we're going to support Fortran. Could we consider supporting something else, or opening up the door to inventing a new language? I think that supporting other languages that have already been well described may be a better path for us, or working with universities are working on ideas, and we provide the hardware support for the language functions. I think some of the managed code is a very important thing. I was asked about Java, and there's also C#. those are important directions for us to go, and they really need to have a concurrent and parallel version as well, and that's still to be defined. It's hard enough taking a language that already exists and adding really small amount of things to it. CUDA, there's an amazing amount of headwind to get acceptance for CUDA, given how familiar it really is to what people already do. If you invented something entirely new, it's a massive evangelism effort. So I think we'll be a sailboat, we'll follow the wind. A question in the back there? So the question is, I showed a lot of applications that had great speedups with CUDA. Am I aware of ones that don't, or are there characteristics specifically that tend not to map well to GPUs? I'm not aware of any of those. In fact, every time I see one, I promptly forget it. No, there certainly are applications that don't do well in the CUDA environment, and some examples of characteristics that don't map well to GPUs are, for one thing, if the problem is just not big enough to benefit from thousands of way parallelism, then you get eaten up by the overhead and the housekeeping and data transfer, because you don't really need that much computing. If the whole execution only takes a few seconds, there's not much speedup really to be had. Other kinds of things that tend to struggle to get speedups from CUDA are very, very large data set sizes, where even speeding up the calculation doesn't speed up the overall throughput because maybe disk bound or network bound anyway. Third category that we don't see a lot of speed up is where the parallelism is not easily apparent in the algorithmic approach. In other words, it's very hard to unweave the different parts into parallel quasi-independent threads of execution. And so old legacy spaghetti codes are very hard to parallelize. And that's not just a CUDA problem, but it's worse with CUDA because to benefit from CUDA and GPU computing, parallelism of 2 to 4 is not interesting. Parallelism of 10,000 or hundreds of thousands is very interesting. And a lot of applications, it's very hard to extract that form of parallelism, or at least to recognize it.
So is it fair to say that codes in which it's worth it to take the time to parallelize the code, use MPI, and run it across hundreds of processors would be worth going to that and optimizing on those GPUs?
Yeah, so the question is, codes that have been worth the trouble to parallelize and port to MPI, are they typically good candidates for CUDA? Often, again, if there's enough parallelism and if there's enough computation to merit all the floating point on the GPU. The question is, will we do something like AMD and Intel have done maintaining numerical libraries? Yes. So yes, we already provide some numerical libraries, and they're gradually increasing in number. We have things that are robust and in production used in real products. So we have a small number of libraries, and we're continuing to add more. If you're asking, are we going to implement MKL? I don't know. Is that, am I answering that? But clearly, I think one of the big things that we can do is there are thousands of libraries in common use for various numerical techniques, and we can't write them all, but we can enable other people to write them. And when we have 80,000 employees like Intel does, we can have 100 people working on libraries, but we can't yet. I dream of that day. So. Yes, on Windows we plug into Visual Studio, and I forget what we integrate with on Linux, but we integrate with a couple of different products. So I don't know. It's not my area. I'm not familiar with it. Okay, file a bug report. We'll treat it as an enhancement request and see what we can do. Okay, so see no more hands, and it's 5:30, so maybe it's time for the reception. Thanks.